Okay. So in this exercise, you only have one question. So basically, they just solving the wave equations with a vibrating string. So let's start with part A. Right, so first of all, so what is the wave equation? Hello, any suggestions? So you have the U xt here that represent the vertical displacement of the element. Then how about the wave equation? Yes. So it is u t t equals to c square u x. And here the c represent the propagating speed of the wave. And then you also have other equations. So you also have the boundary conditions. So here you have the string to be fixed as x equal to 0 and also free at x equals to L. So for the first case, you have u 0t equals to 0. And then for the other end, what is the boundary condition? So here you have the another end to be free at x equals to L. So what is the corresponding boundary condition? Just feel free to speed up now. I supposed to able to hear your voice.
Is it U underscore T?
You understood T?
Yes, and L T equals GX.
Equals to Gx?
Yes.
But now I'm talking about the boundary condition. But the Gx
Oh,
here is the
then
initial condition.
then that is U of LT equals f of x.
U of Lt
Yes.
equals to double x. So the very first thing is you should recognize you have the x here, but the x here is a fixed value, so they just can simply equal. So it's a function of t, but here you have a function of x, and for the another boundary condition is it is about the another end to be free, which means it does not have any external force on it. Utt equals 0. Um, uh, could be u because utt is it just the acceleration, and it's also proportional to the force. But the problem is you don't know. So the very first possibility is you don't know u. So you also don't know utt. So actually for this boundary conditions, it is actually the spatial derivative of u to be equal to 0. So what it means is So here, so you will have one end here. Wait. So suppose you have a string here. Then if there's one end here without any external force, it actually means the the end here will be horizontal. So you have the spatial derivative here to be equal to 0. And the reason is, so as you remember, when you derive the wave equations, then you can, then when you just consider a an infinitesimal element, then you have a tangent here. Then the force. So here you have theta 2, and here you have theta 1. So the net force is equal to T sine theta 2 minus T sine theta 1. And after some approximation, then you get the wave equation. But now when you consider the end here, because at the endpoint here, so you just consider this element here because you only, because it's at the end, so you only have the tangents on one side, and on the other side you don't have any force here. So if at this end the wire or the string is not horizontal, then it will produce some net force upward without any force to balance it. And then because for this differential element, its mass is tends to 0, then if you have a net force here, having some angle here, then it will accelerate this element. Then this element will have an infinite acceleration. So that's why if there is no external force, then at the endpoint, the string has to be horizontal, and the tension will be pointing to the right. And of course, you need to have some, for example, a frictionless rod to hold it. So that's the reason why having a free end implies the string to be horizontal at the end here, and therefore you have the spatial derivative to be equal to 0. Okay, so does it make sense? Okay, I'll take the silence as yes. Then let's move on. Okay, so besides the boundary conditions, we also have the initial conditions. So here we have the initial displacement to be equal to fx. So it is u x0 equals to fx. And the initial velocity to be equal to gx. So it's ut x0 to be equal to gx. Okay, and so this is part A. So basically this is all the equations that we need to solve the problem. We then moved on to part B. Okay. So for part B, so we want to solve and find the normal modes of the vibration. So what normal modes mean is the vibration have a single frequency. So okay, so this is a differential equation, and this the boundary condition and initial condition. So the first thing that we want to do is to use a separation of variables to write the solution as a product of a function of x and a function of t, and then we substitute the solution into the differential equation. Then we have x t prime prime equals to c squared x prime prime t, and then we can rearrange the terms. So for the c, you can put it on either way. The answer will not change, but let's just follow the lecture notes to put the c squared uh, next to the x. Okay, so because the left hand side is a function of only depends on x, and the right hand side only depends on t, so we conclude them to be equal to some constant. For this constant, it um, it can only be negative. So it is similar to the case that we uh, in the diffusion equation. So we write it as minus omega squared to denote this constant to be some negative number. So if it's positive, then you will get some unphysical solution. But what we want is the physical solution. So we write the constant to be minus omega squared. And later you will find that actually this omega is equal to the angular uh, frequency of the oscillation. And that's why we use the symbol omega here. Okay, then as first, let's solve the spatial part. So for convenience, we also write it as k squared x, where k equals omega over c. And actually, the k here is also called a wave number. Alright, so what is the general solution of x?
A sine omega over c times x plus b cosine omega over c times x.
Yes. Right, and then the next thing to do is to impose the boundary condition here to get the eigenvalues. Right, so for the boundary condition here, because it is written um, as as a function of u, and then we have to translate this boundary condition into the form of something that is written um, as something of x. So what you have now is the boundary conditions. They are x of 0. I just see I just saw a question in the chat, but please type it in public next time so everyone can see it. Right, so the question is, do we need to do all the cases in our homework? I mean the separations, ODE equals some constant, and that constant greater than 0 or equals 0, smaller than 0. So do you mean Homer 2? Let me take a look at Homer 2. Uh, so so usually you do not need to consider all of the cases, but just be careful not. So here, so for the questions that you are already familiar with, for example, for this type of trivial questions with a breathing string, then you can uh, just assume the omega, I mean the constant here to be some negative number without considering other cases. I mean, if they are already in your lecture notes, then you don't need to redo uh, the other cases. But just a reminder, uh, so if you so not every problem uh, so for the physical solution not so for the physical solution, not every problem has a trivial uh, domain of the of this constant. So there are actually some problems which have the physical solution in all the domain. So you just assume the constant can be 0 sometimes. Yes, and it can also be positive sometimes. So it really depends on the differential equation. So there could be some extra term here that will make the problem more complicated. So just don't naively think that for every problem, the physical solution must have the constant to be negative. So if it is not, so if the differential equation is not as simple as this, then you have to be more careful. But if we just the simple differential equation here, then you can just simply ignore the case when the constant is 0 or positive. Okay, and let's move on. Alright, so the second boundary condition is derivative at L to be equals to 0. And then we just impose the boundary condition to get the eigenvalue and eigenfunctions. So impose the first boundary conditions. Then we have x of 0 equals to a sine 0 plus b cosine 0 equals to 0, which means b equals to 0. And then we impose the second boundary conditions. So we have b equals to 0 here, so we do not have the cosine term. So x prime of L equals to a omega over c. Here, so we take the derivative cosine omega c L equals 0. And then this can be 0, so we have the cosine term to be equal to 0, which implies omega L over c equals to what?
2n plus 1 times pi over 2.
2n plus 1 times pi over 2. Yes. So what are the possible values of n?
Zero, 1, 2, blah blah blah.
Yeah. So we have the eigenvalue to be 2n plus 1 over 2 and c over l. Oh, actually, I prefer to write m plus, sorry, plus 1 half pi c over l. And the corresponding eigenfunction is sine omega n oh, omega n over c omega n over c x. Yes. So this is the spatial part. And for the temporal part, here is t prime over t equals minus omega c squared. Then for each eigenvalue, we have a corresponding temporal solution. And the general solution is En sine omega n t plus En cosine omega n t. So the so-called normal moles are u x t equals to En sine omega n t plus En cosine omega n t times sine omega n over c x, where omega n equals to n plus 1 half pi c over l. So this is a so-called normal mole. But we are also asked to uh, compare with the case with the same name, but with the 2 points, but with the 2n being fixed at 2 endpoints. So does anyone remember the solution? So this is the case with one n being fixed and another n being free. So how about the case with 2n fixed? So does anyone remember the solution? Yes. So for that case, the omega n is n pi c over l. So the difference between the two solutions are there will be some phase shift in both the spatial part and also temporal part of the two normal modes. Okay, then so the final part, let's see, to solve the entire problem. Okay. Right, so we have the normal modes here, and then the next thing we need to do is to solve the coefficient an and bn. So in order to solve the an and bn, we have to impose boundary conditions. So we have u x0 equals to f of t, f of x, yeah. And then we also have initial velocity equals to g of x. Alright, so the general solution would be a superposition of all the normal modes. Then now we have to match the initial conditions. So root of x of 0 equals to the sum of all these normal modes, and then we set the t to be equals to 0. So we have e and side omega n over c x equals to f of x. Alright, so how do we solve the bn here?
By orthogonality.
Yes. So basically, it's just to multiply both sides by the another eigenfunctions. And then you should remember what is the inner product between the eigenfunctions. I mean, the norm of the eigenfunction. So we integrate from 0 to L. Right, so the eigenfunctions, they are orthogonal, but they are not necessary to be orthonormal, which means that their norm does not need to be 1. So what is the norm of the eigenfunctions? So any idea? What's in the product? The side of the two sides here. So if they're n and m, they're equal, then which means then that's what I mean that the norm of the eigenfunctions. So what is the norm?
Is it L over 2?
Yes. So we have L over 2. Also again, don't naively think that for every eigenfunction problem, the norm has to be n over 2. So if you see you encounter another problem, then you should evaluate the integral yourself. Just don't extrapolate the case here to think that for every eigenfunction with the length to be L, then the norm has to be L over 2, but it does not have to be the case. Right, so this in M. Right, so this is the pointed delta function. So we have the Bn equals to 2 over L. times this inner root. Okay, so this is Pn, and the remaining part is An. Then we impose the another boundary condition. So first we take the derivative. This is a normal mode. Then after we take the time derivative. Then we have cosine here. Then we have the sine here, and then we substitute t to be 0, which means the sine 0 here. Then the terms here will vanish. So we only have the an and also omega n here because we do the derivative. So we have the omega n here. So we have ut of x0 equals to a and omega n sine omega n over c x equals to gx. And similarly with by the orthogonality property, we have uh, L over 2 a n omega n equals to a to this integral. So a n is equals to 2 over L omega n. Where omega n equals to n plus 1/2 pi over L. Where do we have a C? Yes, we have a C here. Yes. Okay, so any questions? I guess not. So you're also welcome to ask anything that regarding the lectures or the homework that you, which is due tomorrow, I think. Yes. Okay, I guess there's no question. Then, alright, so could you please repeat the reason why? So I just saw a question in the chat. Alright, so could you please repeat the reason why ux, the spatial derivative of u equals 0 for the boundary condition? Okay, so here the boundary condition is it is a free end at x equals L. So now we can consider, right, so we consider a differential element at the end here. So free end means there is no external force at the end here. So if ux is not equal to 0, then it would mean at the end here there will be some non-zero angle here. But because it is at one end, so you only have the tension that pointing to the right hand side without any force on the left hand side to balance it. So you do not have any force here. So if there is an angle here, then you will exert an upward force on this differential element. But the differential element here we consider is a very small element, which means its mass is very close to zero. Then if there is a non-zero force here, then it will exert an infinite acceleration on the mass here. So for the case having no external force here, then at the end here, then the string has to be horizontal. And actually you have to, there is a rod here, a frictional rod here, which you can balance the horizontal component of the tangent. But if there is an angle here, then because the rod here is frictionless, then it will not have any force to balance the vertical. So that does not have a force here to balance the upward tension here. And then you will accelerate the element, then you will have an even acceleration here. And that's the reason why it has to be flat here. It has to be horizontal. Okay, so does it answer your question? Okay, so I see another question. I want to ask question 3 of homework 2. Okay, so what is your question? I worked out the general solution of the equations and okay, so just a reminder, so please type your question in the chat so everyone can know what is your question. Actually, can you type your question in public so everyone can know it? All right, so I will copy and paste your questions. Similarly, I cannot copy and okay. So what do you mean? After I want to read off the constant.
I actually want to ask, because I solved the general solution, but in the last part that I had to solve for the constants, just like how we did it in the lectures and in the exercise class. However, it has given us the initial condition where if known function is explicitly written out, and I want to read off the constants instead of calculating them. But I don't know if it's the right direction because when I try to decompose the function to a form where the sine cosine matches the one I just derived, it doesn't look very similar. I want to know if I'm going the wrong way.
So I don't quite understand what. So what are the difficulties?
Do you mind if I share it here?
Yes, you can.
Okay, then the only you can share it in the meeting. Then I screen cap. I screen cap so you can see.
Okay,
What...
I think you can share now.
Okay. So this is Q3. Can you see it?
Yes.
The question has given us the initial condition. And I tried to work it out. But here. I have solved till this part where I need to apply the initial condition, and I try to read them off, and I noticed that it is a cube plus b cube. So I try to decompose it, and I find that I'm going into a very disastrous place.
So you're trying to decompose the cube.
Yes, so to match the sine function, but decomposition do me no good. So should I just approach the very normal way of doing the integration?
I think it is still possible for you to expand that cube in terms of the eigenfunctions. It is possible.
Okay.
But of course, you can just do the integral. But there is a simple way to really expand the cube in terms of those eigenfunctions. Right, so this is a homework, so I do not want to directly tell you how to do it, but you expand it in the wrong way.
Okay.
Right, so maybe I can just give you some hints. Just expand the cosine, then it's beautiful, but I don't know it is okay. Yes, it can be decomposed into in terms of the cosine function. Right, so so you have the 1 plus a cosine cube here, so you can actually so So the very first thing that you can do is to write the choosite tube as the product of choosite and choosite times choosite square. Then for the choosite square, you can use a double angle formula.
Like this.
Yeah. Then what's next?
Then let me see. I need to match the sign. So should I use product to sum here?
Wait. So your general solution is in terms of the sign.
Yes.
Okay. So can you show me what are the boundary conditions?
Boundary conditions is here.
Okay, you have to redo the whole question.
Wait. What's wrong?
So can you read what is the boundary condition here? So is they are thermally insulated at
Yes.
both ends.
Yes.
So what do you have here?
Oh, okay. I see. Is it? Let me see. Is it U of T? Is it this?
I would like you to pick it out yourself.
Okay.
But anyway, the eigenfunction should be cosine instead of sine. So
Okay.
yes, so you can expand your initial condition in terms of the cosine, then you can just make use of opportunity conditions to get the coefficient instead of doing the integral.
Okay. Thank you very much.
Okay, so any other questions? Just use all the formula to expand it more beautiful. Do you mean the EI theta? Okay. Yeah, you can. So if there's no other questions, then thank you all for coming. I will see you next week.